Good morning, everybody. My name is Cheryl Sanchez, and I'm going to talk about AI agents for electron microscopy, but generally also what are AI agents, how we build AI agents, and how that applies to different various instruments and how we can use them. So what I'll cover is what is an AI agent, frameworks that we can use, like things like prompt engineering, building your actual agent, why agents for microscopy, different agent architectures, and how we can fine-tune our agent with something such as LoRa. And I do have some Python examples throughout, so if you want to look at like my presentation afterwards, you can look at that. So what is an AI agent, right? So we have some definitions and foundations that I'm going to go over. So defining an AI agent, right? So an AI agent is able to perceive, reason, plan, act, and learn. And this is a loop process, not just a simple one-shot workflow. And this is different than just a single LLM agent call or a chat box, basically, right? So a chat box is you just have one forward pass, maybe an image or a question, and you get some type of output. There's no tools that you can add to these chat box agents. So for example, if we want to query a database, if we want, let's say, it to control a microscope instrument, it cannot do that. And the other issue with that is there's no memory, right? So when we create an agent, we want some type of memory that is stored prior to any usage of tools that we give the agent or within that task. And then the third thing that's actually really important is that an AI agent is able to verify or correct its own answer, right? So it's able to reason within itself and plan and act based on that. Um, so that is just the overall agent workflow. Now we can jump from different LLMs. So we can go from a basic LLM to a multi-agent system. Now this basic LLM is just stateless, no tools, no memories, no planning, what I mentioned before. Now, if we add a tool to an LLM, it still is not an autonomous agent. It's just an agent that can call functions, APIs, kind of create some type of generation and has a single pass intent. Then we start to give it memory, right? So when we start to provide memory to our agent, that's when we go to autonomous agency. And this is when our autonomous agent could go into the react loop. Now, the react loop is the reason, act, observe, reason again, self-correct, and it's goal-driven. So apart from the autonomous agents, then we can go forward to something even more complex. Now, this complexity is perfect for when we want to do big architectures, such as systems, such as like controlling microscope agents, calling tools, making hypothesis generation, or etc. Right? So we can go to multi-agent systems, which which create specialized agents that can basically collaborate with each other, maybe even delegate roles to each other, and even verify each other's work so we can have critic agents also. So just quickly going over the React loop here and how that kind of works with the worked example. So we want the agent to reason. So we want the agent to think step by step, decompose the goal, act. So invoke a tool or write a code. So we can give it tools or we can tell it, hey, write a code to for that goal. And then it will observe what the tool result is, update its understanding, and try to do this over and over again. So one work example here is, looking at STEM microscopy is, let's say we have some type of material. We want to look at the D-spacing, conform orientation. So the LLM will detect. So we will have a tool that says detect atom columns. And these are just examples, not actual movements or anything like that. It will observe the actual action. So it'll say, well, based on this result of the image, I find this D-spacing or 247 columns found, and the D-spacing is this. Now, then the agent will be able to reason within itself and say, okay, based on this results, what kind of orientation matches here? So that is one way that we are able to do the React loop. And so the agent loop step by step is just, we would like to have some type of human input. The user sends some type of goal. The LLM thinks and plans. It will execute the tool, observe that result, and then that's done, reply, and it will reply or give us an output based on that. So now this is just the same loop over and over again. But this is just something I kind of want to make you guys understand what makes an agent an actual autonomous agent here. So why agents for electron microscopy, right? There's a lot of data volume, right? So when a user uses a lot of data, makes a lot of data, we can get a lot of images, spectra, diffraction patterns in a lot of sessions, in every session. And then we have to have an expert that actually understands, interprets the HADF, EELS, EDX, diffraction data, and this can take a lot of time, and it also has a lot of specialized training to actually understand that. Now, the other thing is a lot of this data, like the images, the EELS, the EDX, all has a multimodal complexity and they can be correlated with each other, right? So this means that this is we need an expert with cross-domain knowledge, and this is not very easy for a lot of people to do, a lot of scientists, and this takes a lot of time. So I'm sure that if anyone has any actual experience with this, you know that this can take hours and hours of time. So the point here is how can we actually use agents to help us understand this data and to make these decisions better for microscopy? So some of the things that we can actually use agents for in microscopy is automated image analysis, spectral interpretation. We can use a RAG function to grab literature, and using literature, we can also do hypothesis generation. Now, this hypothesis generation will allow the agent to observe the results, maybe like, for example, defect structures, suggest next experiments, imaging conditions, or sample preparation steps. And this also allows us to do multi-instrument orchestration. So we can orchestrate the usage of STEM, EELS, EDX, and any like simulation tools into a single automated workflow. And this allows us to unlock reproducible analysis pipelines. So what are some frameworks that we can actually use to build these agents? So one of, I hear my voice. Um, so I'll just continue. So one of the few examples of these is, for example, these small agents. So these small agents is okay, sorry. A small agent is basically code generation, right? So it's very lightweight. You can use local models. So this is good for quick prototyping. You can basically keep your data secure, and basically, use that to make quick prototypes and make fast workflows for these agents. Now, when we want to go further than just making individual like workflows or quick prototyping, then we can go into LangGraph. Now, LangGraph is a state machine, meaning that it has branching logics. We have nodes and edges. And this is best when we have a multi-system workflow. Basically, like if we want multi-agents to interact with each other, we can basically make a basically more complex branching here. Then if we want these agents to actually create multi-agent conversation with each other, then we can do AutoGen, which is a built-in debate and verification system where agents are actually able to talk to each other. And this is one way so we can have peer review style in agent verification. And just another example, we have Crew AI, which is role-based teams, which basically this is just when we have a whole bunch of agents where they all have their own task delegation. And this is a much more structured research pipeline that basically is if you have specific goals for your agents and you need that, you need all of them to do those specific goals over and over again. Now, apart from all of these different ecosystems, we do have other ones like Pydantic AI, Haystack agents, and these are all just different ways in different ways that we can basically move these agents and how they can talk to each other or interact with each other. And, basically you have to pick your style based on what your goal is. So to go over like something simple like small agents, small agents runs locally, meaning that none of your sensitive data can actually leave your lab. This one is good because it has minimal dependencies, so it's easy to deploy on lab workstations with existing Python environments, so it's not very intensive. And there's a lot of wrappers that you can do with already basic Python libraries. And this one is just really easy. I just give examples of how you can call them, and that's something that you guys can look at later. And then just in practice here, it just shows you how you can easily add tools in a tool decorator. You can run your agents pretty quickly. And this is just a very fast prototype way to basically show how you can make a multi-agent system. Um, the other option is lane graph, which I kind of had played around with more because I think this is better for multi-agent systems, where you can basically have announce that the graph has different branches. We have nodes and edges, and this basically tells us like we give different roles to different agents, and the edges basically tell the agents where it should go and help make decisions between each other. Um, And yeah, so it basically controls where the flow is next. And this is creates an agent loop, and this is very explicit, so it's very easy to understand, especially when you're sharing code with other people. And the other thing about lane graph that I like a lot is that there's a checkpointer. And this checkpointer basically saves the full state after every node. So basically, if you're doing this system over and over for a very long time, and let's say it crashes, we can actually go back to that specific point where we were before it crashed, and we're able to basically restart the experiment from that point. So you're not losing all of your data, and basically you're able to resume where you leave off. So that's pretty nice, I think, for LangGraph. Now, when you are creating your tools, there is something very important to kind of exhibit your tools to these agents, right? And this is called an MCP server. Now, the MCP server is basically an open protocol that was created by Anthropic, and this basically standardizes how the agent connects to tools, data, and prompts, and basically in one interface. So you don't have to hard code anything. You don't have to manually put all your tools. You can just open it up into the MCP server, and your agent is able to access that. And the other thing is that when you have an agent, you can also have multiple MCP servers where your agent is able to call from different servers and get access to different tools. And basically, regardless of who builds it, the agent is able to access it. And this is basically an easy way to basically plug it in and write it once, plug it in, and you can use this anywhere. And this is basically the best way to exhibit your tools, your data to any agent. So this is just some quick things that I had made for students to look at later on, which is how you would want to basically structure your microscopy agent or any agent, multi-agent system. So you want everything to be together in some type of architecture. So you want your prompts and tools to be separated into a nice architecture way. You need your memory, your agent, and your actual agent Python file to actually run it. And of course, you always want an environment where you kind of put your session history, your API keys, any instrumental accreditations. Please don't expose this, and basically keep it all safe. Um, so this is the loader code that basically makes the prompts folder that in the previous slide. So basically, you can, in 3 lines, you can basically change the way your agent change the way your agent behaves without touching Python. And basically, this is just a simple example on how to actually load them into your code. So now we're going to go into agent architecture, right? So there's 5 architecture layers for agents, right? So we have our environment/world. So this is where we actually have the STEM, TEM instruments. We have our databases, maybe some type of high computing clusters, literature APIs, things like that. Then we have our perception layer, which is where we ingest all the raw inputs. So we have the EO spectra, the HADF images, EDX maps, anything of data or sort that we're getting. We have our reasoning core, which is our large language model, which is the basically where we're doing that reactor chain of thought reasoning or any tool selection or task planning. And then we have our memory and state, which is where we just basically have our current session. We want to store all our protocols, our literature, our data sets in some type of database. And then we also have an episodic store, so we can actually store past experiments. And this basically allows us to train our agents on past data sets and also allow it to make better decisions in the future. And then finally, we have our action layer. This is where we have our tool calls, Python code executions, anything like that. We might even write out any analysis reports at the end of our cycle. So to talk about memory systems, right? So memory systems on agents we have three different types. We have in-context memory. So this is when the LLM lives in the context window. So for example, it holds the current image, it gets this recent tool call. Let's say we have some working hypothesis, it's able to have that at that time. But basically this is fast, but when the session ends, all this memory basically is erased. So we have to restart that again. We have external memory, which is a long-term semantic memory, which basically is when we have some type of vector database where we store all the data. So we can store embeddings of electron microscopy papers, maybe some type of protocol or reference spectra. We can use RAG, so we can use a retrieval augmented generation thing to basically get some type of similarity search or literature search or something like that. And this can also persist across different sessions. So this is just a way how you can teach your agent to basically have some memory that it can fall back on or pull from as it's learning. And then we have the episodic memory, which basically records the past agents' runs and their outcomes. And this is basically how we teach our agent to learn from its past experiments. And this also allows us to do some type of benchmarking or understanding of the agent. So we can do things like tool call, result, and the quality score of that result there. And this allows agent to learn for each sample type, basically. And this is just an example of how we can save the session history. And I will just skip over this slide. So I'll go into tool design for STEM or TEM. So basically, when we are creating tools, what you want to do is you need to define your tools in specific ways. So we need to, like, for example, when we are trying to create this MCP server with all our tools, we need to kind of create 5 to whatever, how much you want, well-documented tools per agent. And what I mean by well-documented, I mean that you need to have some type of schema, so some type of declaration where you explain this information to the agent. What is it? What is this tool doing? What's the input schema supposed to be, what the properties are supposed to be, and what the output should be, right? And then basically how to run this tool. Now, this is important because this actually allows the large language model to read the tool so that it can understand what this tool does before executing any code, especially if, executing some type of action on your instrument can be very dangerous or, you need to be careful with that. So this allows the large language model basically to read the tool before actually deploying it. And then the second thing that actually this allows the large language model to do is, for example, if there was some type of crash or error within the tool, the agent is able to go back to that schema and understand exactly what happened, why it happened, and is able to actually fix itself or fix that tool so that it can continue the operation. Here I also have another example of how you can register your tools that can be looked at afterwards. You can do it in 2 different ways, like a JSON schema or a Python handler, and both of these ways basically are great to basically call out the tools. So now I want to go into prompt engineering. I know I'm throwing a lot of things very quickly, but I just want to talk about like what all the systems that you need to actually build an agent and how you build an agent. So one of the most important things when building an agent is actually system prompt and instruction design. So you actually need to establish some type of role or expertise for the agents. And this is the system prompt. Now, the system prompt basically can define rules. So any rules that you want to give the agent, any like analysis protocol, like how do you want to have that agent act if you wanted to have a specific protocol in terms of like if you should describe, measure, retrieve, interpret, or cite papers, things like that. And then you can also do some type of prompt design. So, for example, there are various different prompts like chain of thought, for example, or a few shot examples where you can basically tell the agent, think step by step before answering any input, right? And this can actually allow the agent to increase its ability to reason with its tasks, especially if the tasks are multi-step. So here I just have an example that you can basically make a system prompt that's pretty easy, saying like you are experiment microscopy analysis at the University of Tennessee. Describe what you observe in the image, identify crystal structures and orientation, call tools to make quantitative measurements, search literature, things like this. So you have to lay all of this out to the agent before it actually runs. And one thing about system prompts is if you are making a multi-agent system, you actually need to create system prompts for each of these agents. And each of these have to be detailed in its own way. So you shouldn't really share your system prompts for multiple agents and expect them to all work differently. Um, then we can talk about like how we can basically structure these prompts, right? So for example, I mentioned chain of thought prompting. This basically forces the model to reason before concluding or reason with itself before concluding. And now this reduces hallucinations, improves accuracy within the agent. Especially if it has a multi-step analysis, because agents tend to especially if you have multi-steps, agents tend to either forget a step, hallucinate a step, or just go over that step without even going deeper within its thought process, right? So you don't want a quick response. You want a some type of thought process within your agent. You can also give few shot examples. Now, this option is actually really good because it allows the agent to know exactly how you want it to act, because you can just give it two or three ideal examples, and it basically learns how to examples of how to, for example, like analyze a sample, it should call tools, and it basically learns from this input and how it should actually work within the system. So there are two techniques now when we're making prompts. So we can basically improve reasoning, right? So we can have something called the structure output or the XML tag structuring. So these two structure outputs are like, so we can ask for a fixed JSON shape, and then when this is actually loaded, this can turn free text into something your code can route and store. So basically, it allows the system text to basically understand to basically be in a specific format so that the agent can understand the inputs and have a good output. We can also do XML tag structuring. So this basically wraps the prompt sections into tags like protocol, observations, things like that. And the LLM can actually track these XML delimited sections and without confusing them with each other. So this is a good way to basically to structure your prompts. And basically keep them all separated. And, we can basically tell the agent like what each protocol is doing, without confusing it with each other. So there are very much more prompting techniques. For example, we could do role and persona prompting. So for example, we're saying like, can you explain to me like I'm five or something like that? Or can you act like a first year graduate student? Now, so one of the most famous ones that we like to do is say you are, for example, electron microscopist, or something like that, right? So this basically allows the large language model to act in a specific manner or specific persona. Um, we can give it negative examples. So, for example, a lot of the times we always want to tell the agent what to do, but also should tell the agent what not to do, right? So we can tell it, okay, this analysis is wrong, or this tool call was wrong, and this basically helps the agent learn from the negative examples so it doesn't repeat those again. Um, and then we can do prompt chaining. So basically we can say, analyze the image into separate prompts. So we can do it like in a chain loop or something. So describe, identify, verify, report. Uh, so each step is basically easier for the large language model to get right. So you're not just throwing all of it all at once to the large language model. It's able to go step by step. So one of the most important things about large language models is fine tuning, right? Now, there are different ways to fine tune. And when we fine tune our large language models, we want to basically adapt the large language models to a specific action, right? So when to fine tune, right? So first things first, you don't want to fine tune right away, right? So fine tuning is very intensive, is very heavy. You need a lot of examples to basically fine tune a model. So first, you should always try some type of prompt engineering, maybe benchmark your prompts in different ways, see how you can create a better prompt system, maybe even try different types of prompts or role definitions to see if that improves it. Um, you can do a RAG function. So basically you can ground the model into some type of literature. This is really important, especially if you're doing something like hypothesis generation, where you want the agent to read from literature to actually understand what it's doing and possibly create with some type of hypothesis. And maybe create a more structured output prompting or few shot examples. And all of this can actually drastically improve your large language model, your agent, before actually fine-tuning it. But if you do want to fine-tune your agent, then you need to have a lot of examples, right? So for example, microscopy might be great because you can have maybe 500 plus high quality examples if you're the one getting these samples. But of course, or if you do have a database, which I'm not sure if electron microscopy has a good database, but if you can find a good database, then that's perfect to actually train your model. Um, you do need to have everything in a specific output, and then you need to pick what type of model you're actually trying to fine tune. For example, if you fine tune a 7-bit model versus a 70-bit model, then that is a huge difference, right? So if you fine tune a 7-bit one, it can actually outperform a 71. So that actually matters because a 71 is huge. That takes a lot of space, especially if you don't have a lot of space on your computer. If you're using a supercomputer, it's much, much easier to use a smaller model. And basically, this allows you also can train the agent on specific jargon. So, for example, if you have some type of like instrument brand information that you need the model to understand, any local materials that we can't fully capture. So, let's say we have like a domain like you have a domain experiment that you need to look at that is not widely available, so you want to train your model based on that, or any jargon that the model may not have any access to and has no idea what the heck you're talking about. That is one of the reasons why you would want to fine tune. So what is LoRa or QLoRa, right? So basically, the main idea is you basically freeze a big base model, which is this. Oops, how do I? This big base model, which is this kind of gray area. And then you want to train two small matrices, right? So you have A and B. Um, and basically, you will train these small matrices instead. And you can basically only update like about 0.5% of the parameter, which is very, very small. Um, and that is actually very great because you don't have to take a lot of memory, a lot of intensive space to basically fine tune them. You can fine tune only pieces of that model. And so you're not doing like any heavy work basically. Now, yes, let's go into checkpointing. Uh, So when we're training, so these basically mean the same thing, right? So when we're training checkpoints for the models, we want to go into, for example, every end step of this experiment, we want to train the model with LoRa or QLoRa. And we want the best performing step, basically, to be trained into the model. Not all of them, not just the last one. We want the best performing step. And this basically allows the model to be trained like more nicely. So it's not being trained like on a multi-hour training run and all the data is just being thrown at the model. We can actually just checkpoint it and train only bits and pieces of it. We also can have agent run checkpoints. So after like every node or loop, depending on what your architecture is. So if you're using like small agents or lane graph, you also want to have those checkpoints there that can actually be put into the training checkpoints, and then the agent can also save its states and learn from those states. And this basically allows, you can also add like human in the loop or something like that to basically pause, review, approve, or continue. So all these checkpoints really matter when you're making these agents. Now, this is another example just for, if you want to create your agent. So this is just showing you how you can prepare your data set. So basically, what your data set needs, what kind of materials, information you might want, how you can actually make that make that example in Python so that you can actually, train your model. And that's just an example. So the other thing is fine-tuning isn't just a one-time event. You need to continuously fine-tune your model if this is your goal. If the other options didn't work out and you need to continue fine-tuning. So the whole point is fine-tuning can be kind of intensive because you need to log everything, right? So you need to log every run. You need to basically create and don't dump. So you need to filter all the cases where things went wrong, uncertain, or were corrected, and use that as a way to basically fine-tune the model so the model understands like what it did wrong, what was uncertain, or what it did that had to be corrected. You want to version everything and evaluate before you swap. So basically evaluate each of these new updated models before basically replacing it fully. And this basically allows you to test your model before deploying it. And also you should also keep your previous versions just in case, because sometimes you can train a model and that training actually maybe created a negative impact on that model. So you want to be able to roll back. So how can we build our microscopy agent, right? So let's put it all together. We have a lot of information now. How do we put this all together? So, for example, we can use RAG for scientific literature. So, for example, we have a lot of papers, maybe thesis, handbooks, protocols. We want to split them. Maybe we can use Cybert or some type of library to basically encode them. Or you can use a database. So database is great if you really have a large amount of papers or information that you need the model to understand. And you want to input some type of RAG function so that the model can query and retrieve and basically create answers, context-grounded answers, or even questions to itself with actual specific literature or information that's grounded on the truth. And this is basically an example of how we can do the RAG encode, and this is something to look at afterwards again. And yes, so now putting it all together finally is this is agent loop encode. So this is basically how we're able to create this loop. We have that system prompt, we have our history, we're loading the response, the model, the tools, and all of this is put together so that we can run the actual agent in a loop. And finally, you can run your agent. Now to explain what happens after each iteration, we can send full history to the API or the MCP server. We can tell the model to decides is it done to continue going, basically reasoning with the self. The code runs all the tools. We append the results and we loop again. So this is basically the React workflow. So one way to show like another example of, how the agent pipeline looks like with some code examples is we would tell it to acquire maybe generate some TIFF files or get some images or EDS, EEL, something like that. It'll load it. It'll recreate the React loop. So the agent will reasons, calls tools, observes results. It'll call the tool. So this is through the MCP server. It'll interpret the results based on that and a report. So typically when you're actually doing this loop, you do need to make some type of report. So maybe some PDF or markdown result. If not, then the agent will be running in the background. You really don't know what's happening. So this is actually important too. Now, just an example of an agentic framework that can be done, right? So this is something that we've actually been working on where we show different phases of how the agentic work framework can be created with a multi-agent system, right? So we can have the agent observe maybe some type of image, create an image analysis. We can have the agent based on the input of the user, go through literature search through literature, create a hypothesis, maybe do some type of uh, have a critic. So one thing I never really mentioned here is one of the roles that you can have an agent role an agent can be is a critic agent. So basically it can decide or talk to the other agent and say, hey, I don't really like what you're doing or what you're doing doesn't make any sense, right? So it can go back and forth between them, between two agents back and forth, so it can correct itself and basically allow it to make a better hypothesis or reasoning, something like that. And then we can basically have some type of user validation. So the user will say, I approve this or I don't approve this, and maybe why I don't approve this, and have this go back and forth. So this is a loop within itself. We can then have something like called an experiment supervisor, which basically decides what measurements can be done next. We can also include that with the measurement critic, which says, hey, I don't like the tools that you're trying to call. I don't like, it doesn't make any sense for this specific action or the goal that we're trying to create. So you need to change that. And then we can have execution. So basically, it will actually plan, validate, execute, analyze, and loop over again, right? Finally, we will have something called policy learning, right? So this is where we have all the memory where after it runs the actual loop of this all framework, then we can say what went right, what went wrong, what it should do again, what it shouldn't do again, and basically allow that to train back into the model so that the agent can learn from the experiments. And then we get our final summary. Now, one thing I do want to mention is I do believe humans need to be in the loop still. So for all of these processes, we do have like human in the loop. So for the hypothesis, we want someone to approve it, disapprove it. For actual any tool calling and processes, we also want that to be able to be approved or disapproved from the by a user. And this is basically some type of hybrid architecture where we can have both agent and human in the loop. So I also included some type of like multi-agent patterns for microscopy. So some of the roles that you can have for the agents is, for example, you can have orchestrator or workers. So some type of planning agent that can decompose the imaging goal and delegates to specialized workers. So it basically tells the agents the other agents what to do. So if you need to do a literature search, do that literature search. If you need to make an acquisition, do that, and basically delegates it. So that way, it's more easier for the workflow to go cleanly without any issues, or you don't have the actual, let's say, literature agent making that decision itself. We actually have we can also have an agent that does a reflection loop, right? So a critic agent, it basically proposes some type of structure. Let's say then a critic agent will then check it against some type diffraction pattern, and then it will kind of like review it and see if that makes sense. So it's kind of like a peer review, right? Scientific peer review, but with agents itself. Parallel fan out. This one's actually really interesting to me because you can run independent agents across multiple grids simultaneously, right? So, and then at the end, you can merge those results. So this is really interesting, and I'm not too sure if this actually has been done before. to this extent where you can have multiple agents working all at the same time and then merge the final results. And this is actually great if you have like time costs, that you're kind of worried about, or you want to do more of a faster high throughput screening. Um, and then, yeah, of course, and then human in the loop. So I have other examples here that we can also look at later. Um, so you also need to take in consideration your evaluation, observability, and cost at scale, right? So you want to trace everything. So all of this information you need to basically take into consideration because this matters in terms of your costs, how you're evaluating the actual workflow, if the workflow is actually working properly, right? So you want to do automated evaluations. You want to do like prompt testing, like if I do prompt A, is it better than prompt B? Things like that. Do model tiering. So what I mean by model tiering is don't just use the same model for all of the agents, right? So for example, if I have an agent doing something very simple, then if using Claude, why would I use Opus over, let's say, Haiku, right? If it's so simple. You're gonna use a lot of tokens, you're gonna use a lot of costs for something that's very simple, or the vice versa. If you are doing something complicated and you need a better model, then you wouldn't use a model that's not trained well or very small. Um, and basically, these are different like ways that you can basically take in consideration how you can evaluate your model and how you can also consider like the cost of everything in scale. So some key takeaways here is agents are loops, not just pipelines. So it's not just a straight shot. You have to loop everything together. If you want to create agents, using small agents is a great starting point, and then you can go into LangGraph or the other options. You want to ground everything in RAG. So basically, you want to do tool calling, literature search, all of that. You do need some RAG, and this is great before actually fine tuning. So don't just jump into fine tuning. Also, prompt before you fine tune. Try the different prompting options because the different prompting options actually can drastically improve. I've had this experience where I had one line of prompt that actually degraded my agent like significantly, and I was trying to figure it out, but just by erasing that one line of prompt, it actually changed the agent like completely. So this is something that you need to take into consideration when making your models or your agents. And you also wanted to have reproducibility, right? You don't want your agents to go crazy. You don't want it to just make decisions that don't really make sense. So you kind of want to log everything. You want to have a memory. You want to have a checkpoint because you want it to be reproducible. And always start small. Don't just create like 20 agents that work for one thing that can just be done with one agent, play around with that and before you actually create your autonomous agents. Now, I do have some resources that you can look at to basically look at the frameworks, foundational papers, what models you can use, and some papers where they have science and AI together, um, and basically look into that. And yeah, let me know if you guys have any questions. Nope. Okay. Uh, Annotating few shot examples. I'm not exactly sure what you mean by annotating, but the point of few shot examples is telling it like the agent how its role should be, or example of how its role should be, into the actual system prompt before a running the actual agent. So for example, a few shot example would be, I want you to always, let me think of an example. When you do something, right? Like for example, if I want you to control the microscope, uh, you need to always do fine tune the microscope before running it or something like that. So that's an example of a few shot. And you give these different examples to the prompt system prompt before the agent actually runs. And you can basically give this as like maybe a bullet point or numbering to the system prompt before, and usually give these few shots at the end of the main system prompt. So this is just some information for the agent to understand before actually running or becoming like, running in the loop of the React loop.
The agents or have like so else is important for that and always build like this or something. Like is there great?
Yeah, so for a lot of the agents, so I haven't used agents for exactly for coding, but I do use them for like roles and stuff like that. So one of the things I always do is tell it like give it a persona. So like I mentioned, one of the ways you can do is persona. So I tell it like you are a microscopist, you need your goal is to analyze this or that. I think that's like one of the best ways to basically system prompt the agent because it actually won't veer off and do like other things. It'll like say, okay, this is what I am, basically. So that's what I always do. And I always do one-shot examples also because the agent doesn't exactly know what it should or shouldn't do. So that's like really important, I think. Yeah, so that's where you go into the system architecture, right? So for example, lane graph is everything is separated by edges and nodes, right? And what I mean by edges is like you have your each agent is an edge, and then you have a node, and then you have edges connecting them. So basically, it's like they're all separated with from each other, so they're not overlapping or they're not mixing up in any way, and they kind of have a specific workflow where they flow within each other. So using some type of system architecture is actually the most important thing to make sure that they don't mix up with each other. Yes.
Actually, the logistics was about, for example, for having agent or one agents, we have these several things. Uh, I mean, like the LLM models, it's API key or having key or how to the data server based on unit. That is what we will do the and the start point. We had both ease of use and and it would be actually get the result and performance.
Yeah. So if cost isn't your problem, like tokens for calling API key, then I would say start with that, right? Because we are trying to avoid having to fine tune the agent right away. So doing embedding any RAG or literature search or any data or memory state to the agent is fine initially, and that can actually give a really good result. But if you get to the point where you're like, I actually really have to fine tune my agent, then you need to have a local agent in some way. But that's why something using like architecture like small agents where it's not intensive on your computer is actually beneficial. So you don't have to have anything heavy. And secondly, you don't have to use these big models, right? So you don't have to use ChatGPT or Claude or any of these Opus. I actually recommended some of these smaller models like Quen or Gemma 4, something like that. They're very, so you could get like 7B size. So it's really, really small, like 28 gigabytes or something like that on your computer. So that's what I recommend. Yes.
I know.
Yeah. So the skills can go into the MCP server, basically, if that's something you want to add into your into the agents. Personally, I haven't actually messed around with skills a lot, so I can't give you a deep like understanding on based on that, but I know that's something that is being connected right now a lot recently. Okay. Thank you all.